Okay, so good morning, everyone. We will continue with lecture 28, and we were doing. I think I will introduce joint CDF. Okay, so previously I defined the joint PDF, right? So joint CDF of. So by the way, we are doing multiple random variables. So right now, like we are restricted to 2, but at some point we will do even more than 2 random variables. Okay, so the joint CDF of x and y is given as follows. Okay, so these are the natural extension of the CDF that we know. Okay, from the single random variable case. Okay, it's just that now we have like 2 parameters here. Notations are the same. It's just that now I have 2 parameters, and then now I am asking for x less than equal to x and y less than equal to y. Okay, it's a simple extension of the previous case. And yeah, so by definition, this thing means this only. So this comma here does mean intersection. So that's the same thing being written here. So CDF of x and y is probability that x is less than equal to x and probability that y is less than equal to y. Okay. The above definition is applicable to discrete as well as the continuous cases. So we have seen that, okay, in the even in the single variable case, the CDF is defined like this. It's just that you have one parameter there, okay? So fxx is probably that x less than equal to x. It is also an extension of the previous case that that fxy will lie between 0 and 1. Hello, yeah, please turn off your microphone. Hello, please turn off your microphone. Yeah, thanks. Okay, so the CDF, as usual, like the CDF in the case of single variable, here also the joint CDF. So when you have x and y, we call it joint CDF. So all the time we use the word joint, right? So the joint CDF will also lie between 0 and 1, and that's because it's just a probability, right? So probability values are always between 0 and 1. So that's coming from the axiom, right? So probability is never negative and the maximum value it takes is 1. So that these are like 3. So in the XY case, like this is how we may visualize things, right? Because the CDF will be, let us say, of XY. So this is the CDF, right? So the region that you have to look for is this, right? So x less than equal to x region is this, and y less than equal to y region are this, and x less than to x region are this. So this will be this rectangular region, and since we have no lower bound, it's going up to like minus infinity here, and it's going up to up to in the direction of minus infinity here. Okay, so this is like all the region that is below and on the left of this. That denotes the CDF. Okay, so okay, now we can talk about something called marginal. Okay, so marginal PDF. We know that we sum out the other variable. Okay, so if I have to take marginal of x, then we sum over all possible y, and if I have to take marginal over y, then we have to sum over all the x. Okay, so similarly now we can define marginal CDF. The marginal CDF. So the first of all we need the joint. So the point here is to get marginals from the joint, right? So first we have a joint CDF, which is denoted by fxy, and the marginal CDF denoted by just this. Okay, so these are like the marginals. That's why I don't have y anymore, and this is marginal with respect to x, and this is like marginal with respect to y. Okay, so I can find this from the joint. Okay, so the marginal with respect. So this is the. So if we look into, let us say if I sum over the y, right? So that's the same thing as saying that I put in the joint, I put y to be infinity. Okay, so that's the meaning of summing over y. Okay, so if I put a infinity here, then this is the same thing as x less than equal to x and y less than equal to infinity. Okay, well, I mean, so and this is nothing but just x less than equal to x, okay? Because yeah, you have summed over all the y, so there is no longer like any role of y anymore here. So this this becomes just, so it's like completely now dependent on x, like less than equal to x. So which will be defined as the marginal. Like this is the definition of the marginal, okay? So so this is marginal with respect to x, then it means that you sum over all the y, okay? By taking infinity here in the CDF, it does mean that I'm summing over all the y, okay? Okay, because CDF are cumulative, right? So, and here FYY, if I sum over x, and then the marginal CDF with respect to x will be okay. Yeah, so this is with respect to x, and same thing with respect. So I have just rewritten things that I have discussed here, and like another way to write is like write it as a limiting process, right? So this here infinity is the same thing as I can write this as a limit of fxy where y is tending to infinity, and similarly if I take marginal with respect to y, then I have to take sum over x. Okay, so I take the limit x tending to infinity. Okay, so that's why I compute marginal of y for any y and then marginal of x for any x. Okay, so these are the definitions that we have to remember. Moreover, we have the following property. So following properties are these. So fxy infinity and infinity. It's like all of the sample space, right? So this is the whole sample space. So this is a sample space. So indeed, the probability of a sample space is 1. And other cases could be like minus infinity to y, right? So y it should be 0, right? Because so it's like, so if we write this in terms of probability, then this is like probability. The definition of this is like x is less than equal to minus infinity, and y is less than equal to y. Okay. So what do you think as a set? What do you think as a set, right? So this is like probability of the event that x is less than equal to minus infinity. Okay. So this is the set. We know that these are sets, and then y less than equal to y. Now, if you see this guy, then this guy is an empty set. Okay, because random variables will never satisfy this. So empty. So this leads to whole of these being empty set because this is never satisfiable. Okay. So intersection with empty set, possibly, I mean, not possibly, exactly empty set, and then this is possibly non-empty also, but intersection will be empty set. So probability of empty set will be 0. Okay, so this is like empty set, and same thing we can do it for y. Probability of x and then minus infinity will be 0. Okay, once again this is an empty set. Okay, so these are the properties of the CDF, joint CDF, and what we learned also is how to get the marginals from the joint CDF. Okay. So let us see some example of joint PDF and CDF. Okay, so let us try to reinforce our understanding of the joint joint PDF and joint CDF. So let us say X is some Bernoulli. Okay, so and then Y is also Bernoulli. Remember that we are in a discrete setting right now. Okay, so these are like multiple random variables, but discrete cases. Okay, so we are considering these discrete distributions, if you can recall Bernoulli distribution. So here x and y are independent, and where we know that these p and q values of the Bernoulli lie between like 0 and 1. Okay, so and what is the question, right? So find the joint PDF and the joint CDF for x and y. Right? So the question is asking us to write joint PMF and joint CDF. Okay. So what the question is asking for is these values, right? And since this is like x and y, right? So we have so it's asking us to find determine these values, right? So y equals to y and x. The x values will come from here and the y values will come from here. Okay. And what are the possible outcomes like this? So these are usually like we visualize this as a coin toss. Okay, so it's like in the Bernoulli, right? So in the Bernoulli random variables, it's we can relate it to coin toss. So the outcomes are usually like 0 or 1, like true, false, or something like that. Okay, success, failure, and so on. So here so we can encode these as like 0 and 1. Okay, so X range here, possible outcomes are like heads or tails, which could be encoded as 0, 1, and similarly Y could be encoded as 0, 1, because Y is also Bernoulli, X is also Bernoulli. Okay, so what we are asking for are the values, possible values here. So since this is a joint case, many combinations can happen here, right? So 0, 0 can happen, okay, or 0, 1, or 1, 0, or 1, 1. Okay, so these are the values that we are supposed to find, and that will give us the PMF of the joint. Okay, because we are now doing joint. So this is what we are supposed to find, and since the probabilities are given, so probability, these are, remember, by default we assume there is probability of head, right? So probability of head is P, so the probability of tail will be 1 minus P, and probability of head in this distribution is Q, and probability of head will be 1 minus Q. So this is the data given to us. So the first thing is like to determine these values. Okay, and this is nothing but just doing it a case by case basis, because we can enumerate these 4 cases here that will result. So this, we have to list out the values of these joint cases, and we also have to do the joint CDF. Like once we have the PDF, CDF can be computed because CDF is an accumulation of the PDF, right? Okay, so we have some plan. So let us now go ahead and like write down these values, right? So uh, so what is the first step usually when we are solving is to identify the ranges, right? So the ranges of X and Y individually are this. So the joint range will be like the Cartesian product of this. Okay, so let us write down the joint range. So whenever we want to find PDF, first PDF or PMF in this case, because it's discrete. So first we always write down the range, right? So note that the joint range of X and Y. So the joint range of random variables X and Y is given by, so let us write down the joint range. So joint range is R X Y, which is 0, 0, right? 0, 1, and 1, 0, and 1, 1. Okay. Okay. So so here, like you can identify this as 0 as head and 1 as tail. Okay. So now another thing that is like given to us is that X and Y are independent, right? So this should be helpful in finding the joint PD. So if X and Y independent, we have seen that the PMF will be the joint PMF will be the joint PMF will be the product of the individual probabilities, right? So what do I mean by that? So this will be this Ij will be this, and then right. So this is what is meant by independent, because okay. So since X, Y are independent. Okay, so and this is for Ij values we know is coming from the range. So this is like possible 0, 1 values. Okay, so now this will be helpful to us. So from here now we using this because individual probabilities we know for the binomial. So now it is like it is now okay for us to compute this. So XY, let us say we want to compute 0, 0. So this is like probability X, PX0 and PY0, and binomial PX0 is 1 minus P, let us say. Okay, so probability of So and py0 is 1 minus p. So it's like, okay, so I think the head we are choosing is yeah, that's fine. Okay, so the 0 will be head. Okay, that's fine. So px0 in this case will be 1 minus p, and py0 will be 1 minus q. Okay, it's like the probability of okay, did I reverse this? Okay, I think I reversed this, right? 1 is head and 0 is tail. Okay, so this is like the probability of the tail actually, right? So I mean, it depends, like I mean, we are not given explicitly here. Okay, anyway, so I take it this way. Okay, let us say, so probability of tail would be like 1 minus p, and probability of tail with y will be 1 minus q, because q is the probability of head. Okay, and pxy, let us say 0, 1 is probability, again it's simple, right? So probability x0 py1 is 1 minus p, probability of tail, and probability of head in the q case is just q, right? And yeah, so this way, like we can just do this, and pxy 1 0 this will be p 1 minus q, and pxy 1 1 will be pq. Okay, so these are the values for that we have computed, and this is nothing but the joint PD, because we have computed all these values. So that's fine. Okay, so PDF is done, and now the second part is the joint CDF. So joint CDF will be nothing but the sum of these, right? So we recall that the joint CDF is given by from the PMF. So this is the PMF that we know, right? So this is like PXY, right? That x is less than equal to x and y is less than equal to y. And it's a matter of just writing things up, right? So we can list down some of the boundary cases. So x comma y, if x less than 0. So what is this? Okay, so f x y x comma y, if y is less than 0. So what do you think in the chat? Can you tell me what are these values? And fxy xy if, let us say, x greater than equal to 1 and y is greater than equal to 1. So can you tell me in the chat, let us say I call this 1 2 3. So what is your answer for 1 2 3? Can you tell me in the chat? So first two are 0 0 0 1. Okay, so Jyotishwar 0 0 1. Third is 1. Mehul, yeah, that's right. So first two is 0 and third is 1. Yeah, correct. Okay. Yeah, this was a check that you are awake. Okay. And okay, so so here it will be 0, and here, as you said, is 0, and here, since we have hit all possible values, this will include all possible values, so this will hit the whole sample space, so that will be 1. Okay, so that was okay. So these were the boundary cases, and then for the remaining cases which are not boundary cases, so those cases will be like x is lying between 0 and 1, and because this is like a XY case, right? So in XY case, like you can think of kind of like a rectangular cases, right? So it will be like one side. Like one side you will take unbounded, one side bounded, and then vice versa, and so on, and then both side bounded. So that's why there are a few more cases here. So let me write down the other cases. So for example, this case, let us say 0 less than equal to x less than 1, and y is greater than equal to 1. Okay, so let us see this case. So what is the fxy in this case? Okay, so this is it's good to initially write down these things to memorize. X less than equal to x, y less than equal to y. Now, okay, so so these are the cases now, right? So x is strictly less than 1. So what is the possible value of x now? Only 0 is the possible value, right? So 0 is the, so we have to do the cumulative, right? So we are looking for possible values and sum it up, right? So that's the only possible value of x will be 0 case. So the one case that we are getting here from here is x equals to 0, and y is so like y is greater than or equal to 1, right? So y, like y greater than equal to 1 is like all possible cases for y, right? So it's like all possible cases for y, and this will be same as like -1. It doesn't matter, right? I can even write y less than equal to -1 because y greater than equal to 1, y less than equal to -1. It's combining all cases of y. So this is like we have added up y, right? So we have added all y, right? Because this is binomial, so it's like 0, 1, all possible cases you added. So this guy will just drop off, okay? And you will get something called something in the terms of marginal, right? So marginal will be probability that x is equal to 0, right? So this, you will hit the marginal, and x equals to 0. The way we have taken is that 0 is the tail. Okay, so this will be like 1 minus p will be the probability. So this was nothing but, if you recall, this was the marginal CDF. Okay, CDF with respect to x. Okay, because we have counted all possible y. Okay, so that's what the marginal is. So we got the marginal, and same in the same spirit, we can also have other cases now with respect to y, and x now we allow greater than equal to 1. Okay, so this is and due to symmetry it will be the same, so I'm not going to like do this fully. So this will be 1 minus q. So this is something you check as for x. Okay, so this is same as for x. And so this were like the boundary cases. Now we need to tackle the case where x and y are both between between 0 and 1 case, right? So finally, for 0 less than equal to x less than 1, and 0 less than equal to y less than 1, what do we have? So fxy xy is probability that x less than equal to x, y less than equal to y, and this is probability. Now in this case x can be only 0, y can only be 0, so this is nothing but x is equal to 0 and y is equal to 0, and this is 1 minus p and 1 minus q case, right? And other boundary cases haven't been covered this. So the boundary cases, all, if you see here, like all possible values we have computed, because x greater than equal to 1, greater than equal to 1, also I mean this is inclusive of the case that x is less than equal to 1, y is less than equal to 1, because by then it covers everything. So the cases where we have equality here will give you probability 1, because x taking 0, 1 values, y taking 0, 1 values, it will add up to 1, because that will be the whole sample space. So basically we have everything here to define a valid CDF here. Okay, so this was a very simple example. The important thing that we note here is that we use the fact that that they were independent, and that made our life easier, because then individually we know how to compute the probabilities in the case of Bernoulli. Okay, Bernoulli. I hope I'm not saying binomial. Okay, so we are talking about Bernoulli here. So if I plot these results, then this is how these values will look like. Okay, so these are the CDF values. So if you are in this range where x is greater than equal to like x is greater than or equal to 0 and y and less than 1. Okay, so and then similarly all these cases are there. Remember that this plot should have been a 3-dimensional plot, but we have flattened it out. So these are the heights actually in this region. In this region of the domain, the height of your function will be 1 minus p, 1 minus q. So it should be something that comes out of the plane, and it puts the here. This is also similarly in this region, the height of your function. So it should be a surface plot. Okay, but here we have written it like this. Okay, so that's what is all this thing is like noted here. So it is indeed a 3-dimensional graph. Okay, but here we have written like this. Okay. Now, one of the important result that shows up a lot in calculations is finding probabilities in some rectangle region. If you recall, if you try to observe this, this is nothing but some rectangular region in the domain, right? So x, this is like a box constraint, right? So x is going from x1 to x2, and y is going from y1 to y2, right? So okay, I'm sorry. Yeah, so if I draw like this, then I have regions like this. Okay, so this is like x1, and this is like x2, and this is like y1, and this is like y2, right? So this constraints, if you look at, then x greater than x1 and less than equal to x2. So this is this region here, and this region here is like this regions, right? So this will give you this box region here, right? So this is the region x greater than x1, less than equal to x2, and not intersected, but yeah, I mean they are like, yeah, and then y1 less than y less than equal to y2. Okay, so this is this box region here. And the question is like, what is the probability that of this box region, right? Given that someone has given you CDF, which is fxy, then how can you compute probabilities in a box? Because now we are dealing with two variable. So we have the concept of a box. In the single variable case, remember, we were talking about just probability lying between A and B, right? So we were talking about probability that x greater than A, less than equal to B. Then in terms of CDF, it was fxb minus fxa. Okay, so that was for the for single variable case. Now we are talking about box regions. How do you compute probabilities here? Given that you have the joint PDF, and it looks a little bit yeah, strange at first. Okay, so it's like why it should be like this, right? Instead of minus fxy x1 y2 minus x2 y1 and then plus x1 y1, like what is going on here, right? So we will try to like show this proof rather quickly. So this is what we are supposed to find. Okay, so this is the green region, the probability that we are supposed to find. So what we can do is like we can do it in an iterative way. So let us do one by one. Let us see what is this, right? So this region will be this region, right? So this is like this region, if you think of, so this is like fx y and then x2 y, right? So this, so I mean at this point, right? So this will be this region, right? So this will cover all the region, right? So everything, because this is what I mean, the fxy means like probability that x is less than equal to x2 and y is less than equal to y2, right? So there is a no lower bound here now. Okay, so in this case, although we are interested in computing exactly within this, so we also need some kind of lower bound here. But the first step is like I add this term which computes everything below this. Okay, below this and on the left of this. So this will include all the green region up to infinity here. Okay, and up to infinity here. Okay. So first term, now we will subtract the excess term, right? So the excess terms using this x1, x2, y1, y2 coordinates, right? So we have to subtract this excess because ultimately we have to arrive at this region. So we have to do subtraction of some regions here, some region here somehow. Okay. So that's why this second term will now come to compensate for some excess that we have computed. Okay. Now, if you look at x1, y2, x1, y2 is this, right? So this is the x1, y2 here. Now, if you compute fx y x1 y2, then this will be regions that are going from here to here, right? Okay, so this will be regions that go from here to here, right? So so this will be this region, right? So if we subtract this, then the excess that we computed, this green region that we computed, this is now being subtracted from, because this was unnecessary, right? This part got subtracted now, but what we will be left with is now still this part, right? So this part is still left. Okay, so we will try to subtract again x2 y1, right? So x2 y1 will be this guy, right? So this is like x2 y1. Now if I subtract this guy, then obviously so x2 y1 will be this part, right? I mean this part and then this part. So x2 y1 will be this part and then this part. So this will be the problem in this case is I'm getting rid of this guy, which is what I want. But the problem is that I have subtracted this guy now like twice. Okay, so this region got removed twice now. Okay, because of this guy. Okay, so to compensate for this guy, which was removed twice, I add back this x1 y1. Okay, so this was the point x1 y1. If I add back, then I compensate for that. Okay, unnecessary deletion of this 2 times, and then I'm left with only this. Okay, so this is the plan, right? So now let us so I subtracted this. This means that the whole green region has been like added. Okay, so this is this part. For the moment we are at the green region, and then if we did this subtraction, then we are left with this area now. Okay, and if we did this subtraction, okay, then actually this area will be gone. This area will be gone, but apart from this, this region also is gone, because what we are subtracting is x2 y1, right? So x2 y1 is this one. So x2 y1 is this one. So yeah, our desire was to just remove this, but since x2 y1 is whole of this also, all the left and all the below region, so this was deleted unnecessarily. Okay, already deleted and again deleted. So this we put it back. Okay, so we put it back in this pink region that you think of. So if we add it back, so that will be the x1 y1 term here. Okay, so we add it back to avoid double duplication, double deletion. So and then after doing that, we will be left with only this region. Okay, so that's why this explains the pictorial proof of this formula. Okay, so if you, it may not be like needed to or if you want to remember this, then the best way to remember this is like identical terms are added. Okay, so identical IDs. So x2, y2, x1, y1 are added. So first of all, you remember that there are 4 terms, and x1, x2, y2, x1, y1 is added, and the mixed terms like x1, y2 and x2, y1. So these are the mixed terms are always subtracted. So if you want to remember this formula, then that would be a way, or you can also derive this quickly. Okay, so this is the proof of this computing the probabilities in the rectangular region. Okay. Okay, so now let us do some example. So here I roll a fair die and let x be the observed number. So the outcome here could be 1, 2, 3, 4, 5, 6, right? So the question is find the conditional PMF of x. Okay, so this is like I have not yet defined conditional PMF, but I'm trying to recall. Okay, I'm trying to recall the conditional for single variable that we did, okay, previously, and this will give me a motivation. This is just to recall, and then this will give me a motivation to define conditional PMF for the joint cases, right, for multiple random variable cases. So which will be a simple extension of this. So let us try to recall by solving this problem, right? So I roll a fair die and let x be the observed number. So the range of x we know in this case is like 1, 2, 3, 4, 5, 6, right? So range of x is 1, 2, 3, 4, 5, 6. Okay, these are the possible outcomes of a die, and the conditional that is given to us, we can treat that conditional as some event where x is less than 5. Okay, So the observed number was less than 5. That's the condition that we have. So what we are supposed to find is the probability that x given a. Okay, and let us say one by one we can like try to estimate. So what is 1? So what is the probability that x is equal to 1 given that happened, right? So these are the things we actually know. So probability that x equals to 1 given x less than 5 is probability that x is equal to 1 and x less than 5, right? So and then we have to divide by the probability that x less than 5, right? So this is the A event that we are talking about, right? So this is the A event. So and then like this is like simple case. I don't have to like so this is like probability that because end of this is 1 and probability that x less than 5 and this is 1/4. And similarly we can compute the other cases. For example, 2 is same as 3 until it hits 5 because then there will be empty, I think, right? So the end will be empty. So until 3 until 4 will be just the same. Okay, and probability that x given a 5 and probability that x given a 6 will be 0 because here you will have 5 and less than 5 and 6 and less than 5. They will not produce any event, so that will be empty. So that was just a quick reminder of the conditional. Now let us now define in the case of joint. So I'm still going to like in some sense recall. So probability that x given at event A has happened is the same as this, and this is defined as this, and the conditional CDF is defined like this, right? So you can also talk about conditional CDF. So this is the conditional PMF. Okay, so the probabilities when some event has happened, and then here this is like the CDF. So given that A has happened, what are the cumulative probabilities? So we can define like this. Okay, and this has been defined here. Okay. So conditional. So now in case of two variable, we can extend this to the case of x and y rather than saying x and event. We can easily extend this to x and y because x given some y is equal to something is nothing but an event itself. It's just that I'm using the random variable y in place of a now. Okay, so for discrete random variables x and y, the conditional PM of x and y is given as this. Okay, so it's just that the notation has changed. Okay, so here instead of a, I'm now talking in terms of some other random variable. Okay, and I am using arguments like this. So this means like this is the joint. Okay, and then divided by the probability py of yj. Okay. So that's how we extend that to, and similarly, y given x also we can talk about, and that will be this. Okay. So also we can define independent random variables. Like this concept I have already used in the Bernoulli example, but yeah, just formally like I can define this that two random variables are independent if the joint is product of the marginals. Okay, in other words, x and y are independent. Or I can also write this in terms of CDF actually. Okay, so CDF also we can write in terms of like fx. So fxy is the product of the CDF for all x and y. So the proof, another way to say independence, remember, is that the conditional is just the probability of x, right? So if x and y are independent, if the event that the yj has happened has no influence on xi. So this is the proof of that, right? So x given xi, x equal to xi given y equal to yj. This is the definition we are using, and then yy gets cancelled, and we are left with probability x given xi. Okay, so that's another criteria of checking the independence. Okay, so let us see an example of conditional PMF. Okay, so let us consider this problem. This is the problem. So you can see like this is the set and xy, and here x and y satisfies this condition. Okay, so this will determine what are the possible values of x and y that can be taken here. Okay, so if you like see what are the possible values x can take, so x can take possible values 0, 1, -1, and then 2 and -2. These are the possible values x can take. And individually I'm talking about, but it's about joint here, right? Because if x takes 2, then y has to take 0. Okay, y has to take 0. There is no other option for y. So it is dependent, right? But if I'm right, then these are the possibilities, but jointly they have restricted values. It's not really the Cartesian product of x and y. So the possible values of G, the range of, I mean, not range, but the G set itself. If you see, the values will be, so 0, 0 will be allowed because that is less than 2, and 0, 1 is allowed, and 0, 2 is allowed, and 0, -1 is allowed. Okay, and 0, -2 is allowed, 0, yeah, that's all. Okay, and then you go for 1, 0 is allowed, and so on. Okay, so number of possible x and y which satisfies this would be, if you do this calculation, it will be 13, right? So if you do this all possible counts, it will come out to be 13. Okay, so you can verify this. So these are the possible values that you have. Now, if we pick a point xy from this grid at random, okay, so this is the grid of lattice points, and then we pick a point at random, then the probability is 1/13, because 13 are the total number of things, and each are equally likely. So 1 out of 13 is the probability. And find the joint and marginal PMF of x and y. So that's the question. Okay, joint and marginal PMF of x and y, and find the conditional PMF of x given y equals to 1, and are x and y independent. Okay, so that's the question now. Okay, so what we are supposed to find is the joint and the marginal PF. So the question is asking for PXY and the possible values of x, right? So it's like x equals to xi and y equals to yi. Okay, so the possible values of x and y, I have told you, like, it's those possible values which satisfies this, right? So you have to list out all these values. Okay, because this is discrete, then you should be able to list out this in a finite time, right? And so joint will be found from here, and marginals, like marginal, if I have to compute, then so what was the formula for marginal? If I want only pxxi, right? So this is the marginal. Then I know that once I have formulated the joint, then I write x. So in short form, I can write xi, yi. Okay, if it doesn't confuse. Then to get marginal with respect to x, I have to sum over yi. Okay, so that is the marginal with respect to x. And similarly, we get marginal with respect to y by summing over the x. So we have figured out how to do the marginals as well. So the first step is this, second is the marginal. And then we have to do conditional PMF of x given y, right? So conditional PMF of x given y, right? So in other words, x equal to xi given that y is equal to 1. Now we have to compute things like this, right? So this will be using this because the conditional formula we know, right? So this is like the joint and xi given yi, I mean, and y equal to 1. So and will be just 1 here, okay, in this notation. And then this is like the py, so py at 1. Okay, so this will give us the conditional, and we have to vary all I for x, because we have to list out because we are asked to find the PMF. So PMF means that we have to find this formula for all x values, all valid values. Okay, y is fixed anyway, so the only thing that is varying now here is x. So that will give us this, and then we have to check whether this is like independent or not. So to check whether this is independent or not, one criteria, if you remember, is like this conditional value that you get, whatever value you get, is it same as xi, right? So that was one criteria where px given y is same as px only, right? So if it is true for all y, then you can claim that they are independent, and otherwise, like if they are not equal for any of the xi, So you have to just find one xi for which they are not equal, then you immediately claim that they are not independent. Okay, so that gives you a counter example for this. Okay, so if I have to do this quickly just for a record, then I will do this rather quickly. Okay, so the first question was joint PDF of this, right? So joint, sorry, PMF. Okay, so we are in the discrete, so it's only PMF is given by, so Pxy xy is 1 over 13 and xy is in G. Okay, and it is 0 otherwise. So any other value, it has to be 0. And to find the marginal, so Pyy, so it's Pxy xi y. Okay, and so like y is fixed, right? And then xi is in the range of x. Okay, and so these are just the formulas that we have noted down. And then for this we have Pxy x and then yi, and this is like sum over yi in our y. Okay, so we have to sum over y now. So if we calculate some of the values, then probability that this is, so if we, yeah, so if we have to compute the marginal, so we have to like compute this using this formula, right? So px of -2 will be px, so -2 and all possible y, right? So once you have chosen x to be -2, then only possibility for y you are left with is 0, right? So hence in this case the sum will contain only one term, right? So in this case it's 1 over 13 because that's the picking one random point is the 1 over 13 value, right? And similarly, like we can talk about probability x -1. In this case, if I've chosen x to be -1, then the possible values for y are 0, 1, -1. Yeah, that's all. Okay, 0, 1, -1. Otherwise, it will exceed 2. Okay, so this is like probability xy -1, -1 plus probability xy -1, 0 plus probability of -1, 1. Okay, so xy. So this is 1 over 13, 1 over 13, 1 over 13. So it's 3 over 13. Okay, and probability that x equals to 0. In this case, you will have a lot more options. Okay, so 0 -2 plus probability xy 0 -1 plus probability xy 0, 0 plus pxy 0, 1 plus pxy 0, 2, and so in this case it's like 5 over 13. Okay, and these are the possible cases. They cannot be 2 simultaneously. That's the thing here, or even 1 2 simultaneously, 1 or 2, right? So 1 or 2 or -1 2 similarly. So these are the possible values that we have. Okay, so if we summarize this, then px I will be 1 over 13 for I equal to -2, and this due to symmetry we can also say that probability yi will also be actually the same for these y values, right? So 3 over 13 for j equals to -1, 1, 5 over 13 for j equals to 0, and it is 0 otherwise. Okay, so this is like the marginals that we have got. Okay, and the second question was about computing the conditional PMF of x given y equals to 1, right? So conditional PMF of x given y equals to 1, right? So y equals to 1. So possible x values are -1, 0, 1. Okay, so we should restrict to these cases. So then probability that x given y and I1, so this is Pxy I1 divided by Py1. So this is 1 over 13, and this is divided by 3 over 13. This is 1 over 3, right? So for those x values that you have -1, 0, 1. Okay, so we have computed the PMF of the conditional. Okay, so of the conditional random variable, we have computed the PMF. And what we observed is that, so if we write down, summarize this, right? So I1 then this is 1 over 3 for I equals minus 1, 0, 1, and this is 0 otherwise. Okay, so what we observe from here is that this itself can be seen as a PMF of some of the conditional random variables. In this case, it's like x given y can be seen as a random variable, and it satisfies uniform distribution here. Okay, so this implies that x given y equal to 1 is uniformly distributed. So is the discrete case, right? Uniformly distributed over the set minus 1, 0, 1. Okay. So that's the observation we have. Now the third question was, is x, y independent? Now, is x and y independent? Then we have to look at these values and check whether like these guys are equal to so is the same thing as asking probability that x given y I like, yeah, so we can put this condition as 1. Okay, let us say, and is this equal to probability xi? Okay, so we can ask for this. Okay, I mean the condition could have been y equal to 2 also, y equal to 3 also, like you have to disprove. If it is not, then you have to find out some example. So like given that we have worked out for 1, like is it already something there for us to claim that this is not possible? Like let us say I was, let us say 1 over 3, right? And probability, so it's already not possible, right? Because probability px where px of I, right? So if you just look at picking one value out of how many? It's like 6, right? Minus 1, 0, 1. How many are there? Yeah. So the possible values of x where yeah, so it's like 1 over 5 or something, right? So possible values of x. So the probability of this will be like 1 over 5, but this we have computed is like 1 over 3. Okay, so this is not equal. Okay, this is not equal for all I. Okay, so this implies that x and y are not independent. Okay, so this is one way like where we can disprove that this is like not independent. Okay. Okay, so so that was answer to the previous problem. Now what we can do is also define something called conditional expectation. Okay, so conditional expectation. Look, all this is a simple extension of the previous cases, so nothing to like get frightened or anything, right? So x and y be two random variable with range x, range y. Then the conditional expectation. Well, we know. Look, we know the conditional PMF, right? So expectation requires PMF, and then you multiply xi in the front, right? So conditional expectation means that I need conditional PMF, and these values I know, and then to apply to get the conditional expectation, then I multiply by xi. Okay, so then x given y will be defined like this. That's it. This is sum over I. That's it. So for expectation, you always need some PMF, and PMF for conditional we know how to compute, as in the previous example. So, and once I have these values, I multiply by xi, and then I get the expectations. That's how it's going to be defined. So this is the case when we had single variable case and some event, let us say, could be given to us. Then based on the event, I can get a conditional. And then, but in case of like, let us say using two random variables, also the conditional can be given like this. We have defined already this and how to compute this in some examples. And you just multiply xi, which is needed in the computing expectations. So like, for example, in this case, one can go ahead and find, this is the same example as before. Now the extension of this is like find the expectation of x given y equal to 1, right? So this is now easy for us because we have computed the we have already computed this, which was 1 over 3. Okay, and it is 0 otherwise. So xi was like -1, 0, and 1. Okay, so this conditional PMF is already known to us. So to find the expectation now, I only have to do -1, 1 over 3 plus 0, 1 over 3, because expectation is like the sum over this, and then plus 1 times 1 over 3. So that gives me expectation of x given y equals to 1. Okay, so I just plug in the PMF and the values of x, and then we are done, right? So this answer is like very easy, right? And we can like extend this further and find something like this: expectation of x given y is lying between -1 and 2. Okay, so here, like in this case, the first step for us would be to find these values individually. Let us say, so x given y, and then this is like xi, and what is given is -1 less than y less than 2. Okay, so we can like evaluate these values. Okay, for all these conditions for y, and once we have these values, again we can plug in xi p x given y, where y is satisfying this, and then we get a conditional expectation like this. Okay, so we will see this in the next class. So these are like rather trivial. I would say that you go ahead and do this already, and maybe I will skip this in the next class. Okay, and then here it's mod, so it's just a mod here. So instead of doing xi probability x given y, you just put a mod here, and that will give you the expectation, and you sum over I. Okay, so this also we can find easily. Okay, so that will be the conditional expectation. I will try to do this in the next class, and then we will see law of total probability in the case of like two variables case and so on. So and then we will do some solve examples. Yeah, few more solve examples on this. Okay, yeah, so we will continue with this in the next class. So let us stop here. Okay. Yeah, so thanks and bye. If you have doubts, then write to us in Moodle. Write to tutorials. You can ask your doubts as well, and obviously you can ask doubts in the class. Okay. So I hope today class was. I don't think there is not much. Okay. So it's okay, right? Okay then. So see you next week. Okay. Not next week, but yeah, next week, I mean, so Monday. Okay. Okay, bye. Yeah, have a nice day.